catch me up, I'm sure. I think it's empty. It might be empty. Silver, more than I bet you wouldn't know what it is. I bet you wouldn't know. What do you think? I should put Madar for. Madar is a name. But Modar is too.
It took me she would have done it. She's like, you should have waited. Wait.
It looks like an A. Or D, it is a D. Come on, man. Look at the email. Has a or at SML.8.
You weren't so freaking big. I think you better learn.
Yeah.
I remember I get the legs here.
And ever since when I was at
It's typical Paul talking trash.
Ain't nothing to rush in here. Ain't nothing special. Well, it can be.
Not only does he talk trash, he's dead too. Super cat, holy shit.
I don't know about all that. Grass ain't always good.
Let's go.
I feel like I have
Some are just a little crazier than others.
I'm listening.
So you get yourself out of one situation, turn around and do things different. Just a little different ballgame.
Typical Paul talking shit.
Huh? What?
I've said it like 4 times.
All of them is undead. What's going on around me?
Selective being at its finest.
Yep.
Do my notes like that on me the other day.
How you doing, Dr. Gobb?
Good. How are you?
Doing good.
How's this message going so far?
Yeah.
It's alright right now.
It's going too fast for me. I'm behind already.
Oh, really?
I don't sleep.
We're going to go to work, make lunch, and give it away.
Started off a little slow, but I'm trying to get there.
I'm trying to stay on top.
I guess like for structure, I was still we're going, so slow, not a lot of
Yeah,
homework, not a lot
In
of
here,
stuff.
yeah, doing good.
It's alright. If it's anything like last semester, we'll pick up.
No, don't do that. It's staying slow, steady.
Yeah, the steam switch competition, the reports, now you're gonna need to, make a lot of work on that. How many of you are taking concrete too? Which one is going faster?
Concrete.
Concrete.
So fast.
Really?
Yeah.
I think it's because our classes are so short.
Yeah.
What am I doing in my life? And then just move to California and be a singer. Well, no, if you want to be a country singer.
I would just want to see. Anybody can sing these days. They got some.
It's only $40.
Or you can do
Not everything's about her.
Or you can do that's like easy to get to right here.
But the concrete will go even faster.
No, let's not go fast. I can't go faster.
Yeah, it will.
No.
There's a lot of things we have to cover. So.
Yeah, or you could work, or you could just work.
Or we could just take our time.
Okay, so good morning everyone. So last time we started solving this example. We had this
compound beam fixed from both ends, point A and point C. We had an internal hinge at point B, and we wanted to solve this example, draw the bending moment diagram using the slope deflection method. So to do this, we just follow the steps that we learned earlier. The first thing, we broke the beam into two members, okay? And we found the kinematic degrees of freedom. This point is fixed, so there is no rotation, there is no deflection. Here you have a hinge, so there is a deflection, okay, the delta B, and there is a theta, but we don't need to know how much is this theta if we apply the modified slope deflection equation on this member, because the moment at point B is equal to 0, because there is an internal hinge there. And then the same here, there is the same delta here, but in terms of signs, they're going to be negative, okay, to the delta that is in member AB, because this one is, if it rotates like this, then it's positive, it's clockwise. It's the same deflection here, but it leads to counterclockwise rotation of that member, so it's a negative deflection. And then point C is fixed, so there is no delta, there is no theta. Again, you can neglect this theta B2, okay? The theta B1 is not equal to theta B2, but you can neglect both of them because the moment at point B in both members is equal to 0, okay? So we only have one kinematic degree of freedom, which is delta B, okay? And then we went ahead and find the fixed end moments in both members, okay? The modified ones, definitely here we're using the modified ones because we're going to use the modified equation here because the moment here is 0, so we have to use the modified fixed end moments. And then we started writing the slope deflection equations for member AB. As you see here, we wrote the modified equation. For MAB, 3EI divided by L, theta A minus 3EI divided by L squared delta plus the modified fixed end moment. And then MBA, the other end, is 0. And then member BC, MBC is 0. It's a hinge. And then MCB, we apply the equation here. Okay, the modified equation again. Okay, this is the modified equation. And this is what we got, MCB. As you see, MAB and MCB are function of delta B. Okay? And then that's the new part here. Okay, we didn't finish that part. That's what we started last time. The equation of equilibrium. Okay? So what is the equation of equilibrium? We said the unknown that we have and the required equation of equilibrium will look a little bit similar. Okay? So here, our unknown was delta B. That means that the equation of equilibrium that you're going to need is delta is a vertical deflection, so the vertical force, B, at point B, it remains the same point, the summation of the vertical force or the shear force at point B is equal to 0. What does this mean? If I break my beam into two members like this, here we have this YBA, and here we have YBC. The summation of those two forces has to be 0, because there is no external force here applied on the beam. Okay? I only had an internal hinge. If there was a support, then the summation of those two forces is not equal to 0. It will be equal to the support reaction. Okay? But here we don't have an external force, we don't have a support reaction, so the summation of those two forces has to be equal to 0. Okay? So as I draw them in this direction, their summation is equal to 0. If you draw them opposite to each other, then you would say that YBA would be equal to YBC. Okay? So this is very, very important, how you draw the direction of YBA and YBC, and then how you write your equation of equilibrium. Here I draw them in the same direction, so their summation is has to be equal to 0. Okay? Let's say you draw YBC like this, then YBA would be equal to YBC. That means that, no, it's not the summation that is equal to 0. It's actually the subtraction. YBA minus YBC is equal to 0. Okay? So depending on the way you're drawing them, your equation, if you draw them both upwards, okay, then their summation has to be equal to 0. Okay? If you draw them one going upward and one's going downward, okay, that means that you understand they should be equal and opposite to each other. So this is what you have, equal and opposite to each other, so just equal to each other, okay? You already put the direction that they are opposite to each other, okay? So I'm just going to put them in the same direction like this, okay? So now, where's that? Okay. That means that our equation of equilibrium says that YBA plus YBC has to be equal to 0. How am I going to apply this equation? Do I have an equation that gives me YBA or YBC? The only equations that we only wrote two equations here. One that gives MAB and one that gives MCB. Okay? When it was related to theta, the unknown was theta, I said the summation of the moments are equal to 0, and I always had those moments in the slope deflection equations, right? But now I need to find an equation for YBA and YBC. Plug them here. Okay? So how can I find YBA and YBC? Do you remember how would you find those? In any problem that we solved earlier. Do you remember when will you need those forces? If you draw the shear force diagram, you would need those forces, right? So do you remember how you were able to calculate those forces? Just from the equilibrium of each member, right? So now I have to draw the free body diagram, the full free body diagram of each of those members. So this member over here, we had a uniform load like this, right? And that force was 10 kilonewtons per meter. The length of that member is 4 meters. Okay? We have an AY, YBA, and then I'm just going to remove this uniformly distributed load and put an equivalent force. How much would that equivalent force be? 40 kilonewtons, 10 times 4, just right in the middle. Am I missing anything here? I'm drawing the free body diagram of member AB. This is the free body diagram of member
Your moment of A.
AB. Exactly, the moment at A. Do you know how much is the moment at A?
20.
Still, you didn't know, you didn't calculate it yet. So just put it in the positive direction, okay? According to the slope deflection notation, okay? So this is MAB, okay? You don't know how much MAB is, okay? But this is now the free body diagram of this member. So now, let's study the equilibrium of member AB. I'm just going to take the summation of the moments about point A equal to 0. What do I have here? Okay? I have negative MAB, it's rotating in a clockwise direction, and then I have negative 40 kilonewtons multiplied by 2. What else do I have?
YBA.
Positive YBA multiplied by 4 meters equal to 0. From this equation, I would find Y, this is YBA. YBA would be equal to just move those terms to the right side of the equation so they become positive. So we have MAB plus 80, and then you divide this by 4, right? So YBA is equal to MAB divided by 4 plus 20 kilonewtons. Okay? I'm just going to say this is equation 3. Okay? Here we have this equation. I would name it equation I here. 1. Okay? And left. So now, what I just did, I just represented YBA as function of MAB. Why is that? Because I had an equation for MAB, okay? That is related to delta, okay? The delta B that we're looking for, okay? Now, I want to do the same thing. Study the equilibrium here of member BC. So I need to draw the free body diagram. So all the loads, I have to draw all the loads here. You have a uniform load. The length of this member is 2 meters, you have 10 kilonewtons per meter applied on it. So you're just going to remove this uniformly distributed load and put its equivalent force. How much would that be? 20 kilonewtons right in the middle. What else do I miss here?
Moment at C.
The moment at C. Do you know how much is this?
No.
You still didn't calculate it, you just name it MCB. Since you didn't calculate it, just put it in the positive direction. What is the positive direction?
Down.
Clockwise. Okay? So now, I need to calculate YBC. So how to calculate YBC?
Summation moment at C.
The summation of the moments at C equal to 0. So now we have, if I take summation of the moments at C, we have negative MCB, we have YBC multiplied by 2 meters. What else?
20. 20 by 1.
That's gonna be, oh, this is negative, sorry. Yeah, this is negative and then positive.
20 by 1.
20 kilonewtons times
1.
meter equal to 0. So from this, you can go ahead and calculate YBC. It's going to be equal to 20 divided by 2 minus MCB divided by 2. So it's 10 minus MCB divided by 2. Okay? So YBC is 10 minus MCB divided by 2. I'm just going to name this equation 4. What would I do with those two equations?
Equal or negative?
Okay. Substitute them back into the equation of equilibrium, equation 1. Okay, their summation has to be equal to 0. So substitute equation 3 and equation 4 into our equation of equilibrium, which is equation 1 here. So what did we have? We had YBA plus YBC equal to 0. So we have MAB divided by 4 plus 20 plus YBC, which is 10, minus MCB divided by 2 equal to 0. Did I reach what I'm looking for? Why I'm writing the equation of equilibrium? What's the purpose of writing the equation of equilibrium? Find delta. Is this an equation in delta? Do you have delta here? So where would you get the delta?
We could solve for the MA and MCB and plug them back in.
Exactly. So substitute equation 1, equations 1 and 2 into this equation. Okay? So we had MAB. Okay? How much was MAB? MAB was negative 3 EI divided by 16 delta AB minus 20, right? So you divide this by 4 and then you add 20. So this becomes, the first term is negative 3 EI divided by 64 because you divided by 4. Okay, so 1 divided by 16 divided by 4, so that becomes 64 here. And then here you have this delta B, and then plus 15. And then the other part here, this becomes 7.5 minus 3 EI divided by 8 delta B. That's equal to 0. So now you have an equation in delta.
I had a plus 15.
Plus 15, where did this come from? We had MAB here. MAB, you had negative 20, right? So we have negative 20 divided by 4, because you have 4 here, right? You divide MAB divided by 4, so you have negative 20 divided by 4, so it's negative 5 plus 20, so that becomes positive 15. Okay? So now you just solve for delta. So therefore, here you solve this equation for delta, you find that delta B is 53.33 divided by EI. Okay? We finally reached what we were looking for. Our problem was finding this delta, the kinematic degree of freedom. Okay? What would you do with this delta now?
Plug it into the. Plug it into the slope deflection.
Substitute it back into the slope deflection equation. So substitute delta B into equations 1 and 2. You would get the magnitude of the moments. Okay? So you will find that MAB is negative 30 kilonewtons meter. And then MCB would be 45 kilonewtons meter. So now our beam looked like this. This length was 6 meters. Now I know those moments. How much is MAB? It's negative. So negative, according to the sign rule for the slope deflection, this came from the slope deflection equation. So negative is counterclockwise. So it's in this direction. This is 30 kilonewtons meter. MCB is positive, so it's clockwise. So 45 kilonewtons meter. Now you can go ahead and draw the bending moment diagram. How to draw the bending moment diagram? Just take the moment at the critical points. Bending moment diagram. What are the critical points here? Just point A and C. What about point B? Point B, okay, is not an end, okay, of a uniformly distributed load. You can think this as just one load. There is nothing interrupting it other than this hinge, internal hinge. An internal hinge you don't, for drawing the bending moment diagram, okay? If there is no concentrated force or a uniformly distributed force that ends, then you don't need to calculate the moment at point B. You can just treat this as one uniform load from the start to the end, okay? So here the moment is 30, negative 30. And here this is negative 45. And then you connect those 2 points by a dotted line, and then from the center here you go up by WL squared divided by 8. WL squared divided by 8. W is 10. L is how much? 6 squared divided by 8. So this becomes 45. So definitely you're going to go up. It's going to be positive, okay? And it goes like this. So that's the bending moment diagram. While drawing the bending moment diagram, you're just going to have to see that the moment here passes, it's 0 here, okay? And then you do the hatching, that's negative here, and that's positive here. Negative and positive. Any question? Yes?
Well, for one, on that one, is that just going to be an eyeball thing? Is then you just eyeball the midpoint of that and use that equation? Or are you going to look for something, like, whenever we get a test, can I just, you expect it's just eyeball and find the midpoint? Or is there going to be anything specific?
Of the dotted line, I think you're talking about.
Yeah, of the dotted line.
So the middle of the dotted line,
Yeah.
you
Eyeball.
That's
We're just
close
gonna,
enough to the
yeah,
middle.
are we just going to approximate it?
Are you talking about, I don't understand, you're talking about the maximum bending moment or what?
You said it's the midpoint of that line.
No, to draw the parabola, you need a third point, okay? The third point is not the maximum point, okay? It might be the maximum point or not. Here it's not, okay? You just find, you have to find, it has to be in the middle, okay? So this part has to be equal to this part. And then you go up by WL squared divided by 8. You have a third point. The curve passes through this third point. But this doesn't mean that this value here is the maximum bending moment. The maximum bending moment occurs at the point where the shear is 0. To find where's Mmax, okay, the maximum bending moment, it has to be, you know, where the shear is 0. So here, this might be a little bit off the maximum point, okay? This value will give you an, you know, approximate value of the maximum bending moment, but it's not the maximum bending moment. I don't know, does this answer your question?
Yeah, that works. Because I had another one, so.
Okay, just repeat whatever you're asking for.
On the question I'm about to ask, because I have a different question.
Okay, different question, okay.
Okay. On whenever we're doing the moments, what's the difference between you saying we use clockwise to determine positive, negative, and you're also saying just looking at it and
Okay.
the bending?
We have two sign rules, okay? We have a sign rule for the slope deflection equation, okay? When you apply the slope deflection equation or you calculate the moment using the slope deflection equation, that sign rule is so simple. Clockwise is positive, counterclockwise is negative, okay? So whatever moment you get from the slope deflection equation, that's the sign rule for it, okay? And then, when you draw the bending moment diagram, no, you don't use the sign rule for the slope deflection equation, okay? There are two different things, okay? You use the sign rule that we used in structure analysis 1. What does the sign rule in structure analysis 1 say? If the moment is going downwards, okay? Whether it's clockwise or counterclockwise, I don't care. If it's going downwards, okay, then it's negative. If it goes upwards, then it's positive. Okay? So now, when I calculated those moments, where did I calculate them from? I calculated them from the slope deflection equation. So a negative here, since this comes from the slope deflection equation, it means it's counterclockwise. So I just draw it as counterclockwise. This one was calculated using the slope deflection equation, so it means counterclockwise. Sorry, clockwise is positive, so clockwise. Now I want to draw the bending moment diagram. Those are going downwards, so they are negative moments. Okay? Clear? Is it clear? Okay. So now we want to move, okay, to a new topic, okay, that was not covered in structure analysis 1 because it doesn't apply to determinate structures, okay? It only applies to indeterminate structures, okay? What is that we want to cover now? It's the movement of supports. Okay? What does movement of support mean? The support is the point, okay, where it constrains the movement of your structure. Like, for example, when we say you have a fixed support, it means that the deflection is 0, the rotation is 0, right? No vertical movement, no horizontal movement, no rotation, right? When we say a pinned support like this, it means that there is no vertical or horizontal motions, right? When we say a roller support like this, it means that there is no vertical motion at all, right? Now we're saying movement of supports. Does those two words, make sense together? Movement of support. The support prevents the motion. Now we're saying, no, it's moving, okay? The support can move. Does this make sense? According to, just basic things, no, it doesn't make sense. But in real life, no, that's actually supports move, okay? And it doesn't mean that your structure went out of equilibrium. It's still in equilibrium, okay? So how can a support move and still a support, okay? Simply, let's see a very large problem here. Let's say you have a real building like this, okay? A building frame like this, okay? And now you have supports here. Let's say you have some supports here. What does this support come from? What is actually supporting this structure that I drew this fixed support? The ground, the earth, right? So is the support, okay? So actually you have some ground here. This is the earth here. Okay? That's the support of your structure. Is the earth, the soil, is it something so stiff, or when you apply some load to it, the tires of your truck, if you just go on the soil, what will happen to the soil? Yeah, it will sink a little bit, right? So actually, this building is much, much heavier than your truck, right? It's a huge building with huge weight, okay? You're just putting it over the soil like this. What will happen to the soil? It will just move or sink down like this, okay? You agree with this? Okay, that depends how much is this, settlement. We call this settlement of support, okay? The magnitude of the settlement of support depends on the type of soil that you have, right? If you have loose sand, you expect this to be large. If you have clay, it's going to be even larger, right? But if you have rock, it's going to be so small, right? But there is some settlement, okay? So actually, the support did move, but the building is still in equilibrium, okay? It just happened that the building moved a little bit down, maybe a few inches, 1 inch or so, okay? You can definitely minimize this by doing some soil compaction before starting the, construction of your building, okay? But even with soil compaction, still, over time, okay, there will be some small settlement of your building, okay? Definitely you're going to study this in Dr. Said in soil mechanics, okay? The settlements, okay, or the deflection in different soils, okay? So, did anyone take this course with Said yet?
Deflections.
Okay, yeah. What would you call this in soil mechanics?
Differential settlement.
Okay, yeah, but do you have like soil consolidation?
Yeah.
Okay, soil consolidation. Okay. So you had experiments how to measure the soil consolidation. You had equations for this, and you actually can measure or have the equation gives you the soil consolidation over time. Okay. So we just need to understand this. We don't need to calculate it, but we just need to understand that there will be some settlement in the soil. Okay. So now, although I'm putting some fixed support here, representing the interaction between the soil and the building as fixed supports, but those supports are going to move down. Okay. So the support is going to move down. The entire building is going to sink down a little bit, okay? Actually, if we have here the loads on those columns is relatively equal to each other, okay? And we have the same type of support, it means that the entire building is just going to move down with the same magnitude at all of those points, okay? If this happens, so there is no differential settlement between the points. So you can just neglect this movement of support. Okay? It won't have an effect on your structure. Okay? The entire building just moved a little bit down. Okay? The problem would happen if you have a soil here. It looks like the same soil, but actually what you have is you have rock here, and then suddenly you have some clay on top of it. Okay? So here, the settlement of this support will be so small, almost zero, because you have rock, okay? Bedrock here. Here, almost zero. Maybe here a little bit. Here it's going to be so large, because you have soft clay. So what will happen is this point is just going to move down like this. It's still a support. It's still supporting the building, but it's going to sink down more than the rest of the supports, okay? So what will happen is your building, the entire building, there will be deformation in that building, okay? Due to this differential settlements between the supports, okay? So, okay, that's fine. No, that's not fine. As you see, this deformation in the building, okay? This is exactly have the same action as if you applied some load on your building, okay? So just having a differential settlement, okay? This is a load in your building that will result in some internal forces, bending moment, as you see here. Just this deformation will result in some bending moment in those beams, okay? So why didn't we discuss this earlier in structural analysis 1 when we were discussing the determinate beams or determinate strains or determinate structures as in general? Because this differential settlement, this movement of supports, has no effect on determinate structures. It only has an effect on indeterminate structures. Okay? Why? Let's draw a determinate beam here to understand this. Let's say here you have a very simple determinate beam. Okay? And then I'm telling you that this point here just moved down. There was a settlement of this support, okay? And there was no settlement here. What would happen to the beam? It would deflect like this. But since it's determinate, okay, this point can rotate easily, this point can rotate easily, it's just going to be straight line, okay? I have this fan like this, okay? And then I move it like this. Is there any internal forces due to this movement? No, it's just a movement with no internal forces. But the problem comes when this becomes an indeterminate beam. The more fixation you have, okay, this moves down now. Okay, it moved down, but it's not allowed to rotate. So there will be some curvature in it. Now it's bending, okay? Here it was not bending, it just rotated like this. Imagine now I'm fixing this, okay? And then I have to move it, so it's just gonna bend, okay? Let's exaggerate here this. It's gonna bend, okay? Because it's an indeterminate beam. There is more supports than needed, okay? So having this deflection, okay, it will result in some internal forces, but here it won't result in any internal forces. Yes, there is a settlement of support, but it doesn't have an effect, okay? In indeterminate structures, this settlement of support has a huge effect, okay? It will really affect your bending moment diagram and shear force diagram, okay? So now, we understood what's the meaning of the movement of support. We took an example here of this movement of support, okay? Let's see another example on how can movement of support happen, okay? Let's say another example or reason for movement of support. So before we continue here, I just want to write this here. No effect of movement in determinate structures. Here, there is an effect. On the moment or the internal forces generally, okay? Another example of what would cause a movement of support, okay? Let's say you draw a beam like this. That's close to the example that we're going to solve soon, in a few minutes, okay? You have a beam like this, okay? I just drew a beam like this. What does, like, when you have a beam like this, it's just a beam in a building. Okay, I just cut it out of a building. Okay, I have this type of supports. Where those supports come from? There is something that is supporting. We said this is the idealized structure, right? In real life, it doesn't look like this. It's not a line. Okay, the supports, there is something that is giving you the support. Okay, so what would that beam be like for in real life, in a real building? Maybe here, this support, maybe you have a column like this. Okay? And then here you have your beam. In this column, maybe it's continuous to the second level or the next level. Here you have some supports. Where does this support come from? Maybe you have another column. That's supporting your beam here, okay? And then we have a support here. Maybe it's a column, or maybe it's another girder, okay? A larger beam, a girder that is supporting this beam in the opposite direction, okay? And then here we have this fixed support. What's that? Maybe it's a column, okay? So here we have this girder. And then you have your loads applied. You have some loads applied. This comes from the own weight of the structure. You're an expert on this from Structure Analysis 1, right? Calculating the dead load, the life load, they would be rectangular, triangular, right? You did this in Structure Analysis 1. You understand all of those things. So now when you apply those loads, what will happen to this beam? It will deflect, right? There will be some deflection. So now let's draw the center line of this structure. Okay, let's draw it in blue. This is the center line. So I'm idealizing this here as a fixed support. I'm idealizing this as a support here. I'm idealizing this as a support here. I'm idealizing this here as a fixed support. Okay? And then, due to the applied load, it's going to deflect. Right? There will be some deflection. The thing is, what do you expect of the deflection here compared to the deflection here? You would say, no, those are supports, right? There is no deflection at those supports. Yes, this is a column, so most probably it's not going to move a lot. There will be some, depending on the normal force, the axial force in this column, there will be a very, very small deformation in the column, right? Do you know how much is the deformation in this column? The deformation here is delta, which is PL divided by EA, right? The axial force multiplied by L divided by EA. It's very, very small deformation, okay? Here, this is a column, it's going to have a small deformation. But here, this is a beam. The deformation here, this beam is going to move down a little bit, okay? Because there is nothing actually supporting it. It's maybe supported at the ends of the girder, okay? But not in the middle. So there will be some settlement compared to those columns. So there will be some settlement of support here. This point, there will be some settlement here. Compared to the other supports. Because it's not a very, very rigid support. It's a girder that can deflect actually a little bit, okay? When there is a load applied on it, okay? The deflection here, you can calculate this deflection according to what you learned in Structure Analysis 1, okay? And in the mechanics of material, okay? Using the conjugate beam, we started how to calculate the deflection this semester, right? So there will be some deflection. So as you see here, the deflection here is going to be so small it can be neglected, but this one is going to be definitely much larger than the deflections here. So this is like a settlement of support compared to those supports. This support will settle down compared to the other supports, okay? So this settlement of support, if this is an indeterminate beam, it will have an effect, okay, on your bending moment diagram, okay? If it's an determinate beam, it will not have an effect. It's an indeterminate, it will have an effect. Okay? So how to take this into consideration? Okay? Just put it in the slope deflection equation. Okay? So let's see an example. Now we understood what's meant by the settlement of support. It's still a support. This girder is still supporting this beam, but the girder is going to move down a little bit due to the applied loads on it. Okay? How can we manage to take this into consideration into solving our problem? It's so easy, so straightforward. Okay? So let's take an example here on how to take into consideration this settlement of supports. Okay? So here we have this example. In the textbook it's 11.4, but I just modified a little bit. This is on the movement of supports. Okay? So in this example, we have a beam that looks like this. Exactly like the example that we just discussed now. We have point A, B, C, D, and we have those lengths here given. This is 7.2 meters, 6 meters, 4.5 meters. And on that span AB, there is a uniform load of 20 kilonewtons per meter. Okay? What's the problem statement here? What are we required to find? We're required to draw the bending moment diagram due to the shown loads. Not only the shown loads, there is also a movement of support C of 30 millimeters downwards. Where did this come from? Just explain where did it come from. Some settlement of that support. Maybe they are all columns and this is just the girder. Okay? And we're given here. This is very, very important. When you consider, okay, the movement of supports, okay, in the previous problems, EI was just a constant value and that's it, okay? It would cancel out, okay? Here, you need to know, okay, how much is EI. So E is 20 gigapascals, and I of this beam is 600 times 10 to the power 6 millimeter power 4. Okay? So now, for the solution. First, we have E and I. Let's just multiply EI, okay? Because we have, 3 EI or 4 EI divided by L, right? We have EI as a constant. So let's calculate this constant, E multiplied by I. So E is equal to 20 gigapascals. Sorry, 200. So this is in the problem here, it's 200, okay? 200 gigapascals. Is this unit, gigapascal, consistent with the units that we have in this problem? What's a gigapascal? It's 200. What's a gigapascal? It's 10 to the power 9 Pascal, right? So it's 10 to the power 9 Pascal. What is a Pascal?
Newton meter.
Newton per meter square. Is this unit consistent with the units we have in the problem?
Almost.
Huh? Almost. Here we have meter, yeah, the distances are given in meter. The load here is in Newton, but the load here is in kilonewton. So I just want to have this in consistent units, so I'm just going to divide by 10,000. Okay, so this becomes 200 times 10 to the power 6 kilonewtons per meter square. Okay, just to have consistent units. Okay, what about I? We have it in 600 times 10 to the power 6 millimeter power 4. Is this consistent with the units that we have? No, the length here is in meters, so the dimensions, the length has to be in meters. So how to change from millimeter power 4 to meter power 4? How to change from millimeter to meter?
Times 10 to the negative
10 to the power negative 3. This is from millimeter to meter, but here it's to the power 4. So it's 10 to the power negative 3 to the power 4, which is 10 to the power negative 12. Okay? So here this becomes 600 times 10 to the power 6 times 10 to the power negative 12 meter power 4. 10 to the power 6 times 10 to the power negative 12. This is how much? 10 to the power negative 6. So now how much is EI? 200 times 10 to the power 6 kilonewtons per meter square multiplied by 600 times 10 to the power negative 6 meter power 4. You have 10 to the power 6 times 10 to the power negative 6, they cancel together, and then 200 times 600, this is 12 times 10 to the power 4. Okay? Kilonewtons meter square. That's consistent with the units that we have in our problem. Okay? So now this is the constant EI. Anytime you have EI, just plug it 12 times 10 to the power 4 kilonewtons meter square. Okay? That's EI. That's good. That's before we start solving. We just calculated that constant, EI. Now, we want to solve this problem. You solve it, okay? Just let me know what are the steps. How are we going to solve it? Using the slope deflection method that we learned.
Break the beam.
So just follow the steps of the slope deflection. Break the beam into individual members and find the kinematic degrees of freedom. Right? How many members we're going to have here?
3.
3. A, B, B, C, C, D. Okay? So 3 members here. A, B, B, C, C, D. Let's find the kinematic degrees of freedom. Point A. What's the deflection at point A? 0. What about theta A? 0. B.
0 and unknown. 0 delta unknown.
The deflection is 0. Theta B. Unknown. Right? What about point B in the second member? The same. Delta B is 0. Theta B is the same value, right? As in member AB. What about point C? How much is delta C? Exactly, it's not 0. It's a support, but you know that this support moved down a little bit. How much is that? 30 millimeters, right? It's 30 millimeters, it's 3 centimeters, so it's 0.03 meters. It's downwards. So downwards, is it positive or negative? This delta. What did we say about delta for the slope deflection equation? If it causes the member to rotate in a clockwise direction, it's positive. Did the member rotate in clockwise direction or counterclockwise direction? Clockwise, so it's positive. Okay? What about theta?
Unknown.
It's an unknown. Let's move to member C, D. How much is delta here?
Be the negative.
So here, delta in this member is 0.03. It's the differential settlement between those 2 points. Okay? What about point C here? It's the same magnitude, but
Negative.
negative, because this member here is going to rotate in a counterclockwise. Okay? It's like this. When this point C moves downward, it rotates counterclockwise. Okay? So here this is negative. So delta here in this member is negative 0.03 meters. And theta C is the same value. Okay? What about point D? How much is delta D? 0. How much is theta D? 0. Okay? What about the second? So now, what are the kinematic degrees of freedom?
Theta C.
How many unknown do you have here?
2.
What are those two?
Theta B, theta C.
2, which are theta B and theta C. What about delta here? It has a value, but it's known. It's not an unknown. It's known. Okay? It's 0 here. It's 0 here. It's not 0 here, but you know how much is it. Okay? It's not an unknown. And then you move to the second step. You start by calculating the fixed end moments. Let's ask a question here, a quick question. Is there any member here that you're going to use the modified slope deflection equation? When would you use the modified slope deflection equation? Let's say if one member you have an end where you know that the moment is 0. Is there any member here that one of its ends, the moment is going to be 0? Member AB, no, the moment here is unknown, the moment here is not 0. This member, the moment here is MB, the moment here is MC, there will be a moment here, the same here. So there is no member where the moment is going to be 0. I find some students, especially in problems like this, they would look like this and say, oh, there is no load here, that means that MB is going to be 0, MC is going to be 0. No, if there is no load, the fixed end moments are 0, okay? The fixed end moments due to the loads are 0. But that doesn't mean that the moments are going to be 0. Because the moments in the member depends on the loads and the deformation of the ends, right? There is a deformation, there is a theta B here, theta C, and theta and delta C. So there will be moments in member CD, okay? There will be some bending moment in member CD. So now, the fixed end moments. We don't use the modified one, we use the regular ones, okay? Where would you have fixed end moments? Only in member AB, because this is the only member that you have loads, okay? So for member AB here, it's how long?
7.2.
7.2. You have a uniform load here of 20 kilonewtons per meter. So there will be some fixed end moments here. WL squared divided by 12 and WL squared divided by 12. So this is 86.4 kilonewtons meter, and this is 86.4 kilonewtons meter. Is this positive or negative? And this is positive or negative? This one.
Negative.
Negative. It's counterclockwise, okay? What determines, what's the rule? You're using this for the slope deflection equation. You have to adhere to the sign rule of the slope deflection equation. Counterclockwise is negative. And this one is clockwise, so this is positive. Okay? So now that means that the fixed end moment of AB is negative 86.4 kilonewtons meter, and the fixed end moment of BA is positive 86.4 kilonewtons meter. The rest of the fixed end moments in member B, C, and CD are zeros because there are no loads. Okay? Now, let's write the slope deflection equations. How many slope deflection equations you're going to write here? 6. You have 3 members. You have to write it at each end of each member. So let's start with member AB. Now I'm going to try to be faster. We did this many, many times before, right? So I'm going to try to make it faster here. MAB. How much is MAB? 4EI divided by L theta A. How much is theta A? 0. I'm not going to write it. Okay? Plus 2EI divided by L theta B. Is there a theta B? Yes, so this term is not 0. So 2EI divided by L theta B. What about delta? There is a term. Negative 6EI divided by L squared. multiplied by delta. Is there a delta in that member? No, so it's just a 0, okay? And then plus the fixed end moment of AB. So here we have 2 EI, okay? You can substitute EI now, just substitute the value of EI at the end, whatever you want, okay? Divided by L, which is 7.2 meters, okay? Multiplied by theta B plus the fixed end moment, which is 86.4 kilonewtons meter. So that's equation 1. Okay? There were other terms, but all of them cancelled. Okay, the two terms, the one that depended on theta A, the one that was related to delta, both are 0. Okay, so I didn't write them. Okay, and then MBA. How much is MBA? 4 EI divided by L multiplied by theta B. So 4 EI divided by L theta B. What about the term with theta A?
0.
Theta A is 0. What about the term with delta?
0.
0. Fixed end moment.
86.4.
There is a fixed end moment at B8. So this becomes 4 EI divided by L, which is 7.2 theta B plus 86.4 kilonewtons meters. And that's equation 2. So those are the two equations for member AB. Let's do the same for member BC. So what we're going to write here, MBC and MCB, both ends of member BC. MBC, you have 4 EI divided by L theta B, okay? So 4 EI divided by L. How much is L, the length of that member? 6, right? 6. Theta B plus 2 EI divided by L, theta C is unknown. What about delta in member BC? Is there a delta in member BC? Yes, there is a delta with 0.03. So it's not 0. Okay, this term doesn't cancel here. What's the term? This term is negative 6 EI divided by L squared. Okay, L is 6. Multiplied by delta. How much is delta? 0.03 meters. Plus the fixed end moment. How much is the fixed end moment? 0. So that's equation 3. So as you see here, you had some given quantity due to the load, the fixed end moment. Here you have some quantity, okay? It's given, it's a number, right? EI is known, it's all known, okay? That is related to the settlement of support. So as if the settlement of support has the effect of a load on that member, okay? As if that member was loaded. There were no loads, but now you have a term that is equivalent to the fixed end moment, okay? And then MCB, it's 4 EI divided by L, theta C, plus 2 EI divided by L, theta B, minus 6 EI divided by L squared, multiplied by delta. And that's equation 4. And here I'm going to stop, okay, a little bit, because this is one of the very popular mistakes that I see on tests, okay? When you put delta here, okay, it doesn't change its sign in the member. Okay, I see some students, when they apply the slope deflection equation at point B, they say, no, delta at point B is 0. So they just put here this delta equal to 0, because the deflection was at point C, not at point B. No, the deflection here, okay, is not the deflection at point B. It's the relative, okay, the differential deflection between the two ends of the member, whether it's at B or at C. Okay? It's not 0 here. Yes, the deflection at point B is 0, but this equation is written for member BC. There is a relative displacement between point B and C. So it's not 0, even if delta B is 0, but delta C is not 0, so there is a relative displacement between the 2 points that you have to plug in. If this is 0.03, it's the same magnitude here. I see some students plugging here equals positive and put it here negative, saying, oh, they are opposite each other. No, the member rotated in a clockwise direction. That's it. It's positive for both points. It's the same member. Okay? See, I'm stressing on this, okay? If you do it wrong on the exam, it's your problem, okay? I'm sure I will see some students doing this wrong, okay? And you know, after the exam, I will have you in my room to see your exam paper. I will just remind you this, okay? So this is, don't forget, a delta is in the member. It's not at the point. If there is a delta in the member, there is a delta in the member. Whether the point moved or not, there is a relative displacement between the two ends of the member, there is a delta in the member, okay? And then let's do member CE. What's the two ends of the member? MCD and MDC. What's MCD? 4EI divided by L. How much is the length of member CD? 4.5. Multiplied by theta D. Theta C, sorry. Plus 2EI divided by L theta D. How much is theta D? 0. Minus 6EI divided by L squared. 4.5 squared. Multiplied by delta. How much is the delta in that member? Negative. Okay? Negative 0.03 meters. Plus the fixed end moment, which is 0. So this is equation 5. And then the other end here, 4EI divided by L theta D, which is 0, plus 2EI divided by L theta C, minus 6EI divided by L squared, multiplied by delta, which is negative 0.03. The sign doesn't change as long as you're in the same member. It's the same sign. Okay? Now, we had 6 equations. We wrote all the slope deflection equations. What should you do next?
Plug in the console. So
We got to find the
Wait, so-
information.
Equations of equilibrium. So the third step, you need equations of equilibrium. How many equations of equilibrium do you need here? 2. Why 2? Because you had 2 unknowns. What are the 2 unknowns? Theta B and theta C. That means that what type of equation of equilibrium you're going to need. If theta B is unknown, how would your equation of equilibrium look like? The summation of the moments about point B has to be equal to 0. Theta C is unknown. How does the equation of equilibrium look like? The summation of the moments at point C is equal to 0. Where did this come from? If you draw the three-body diagram of the 3 members, this is A, B, B, C, C, D. You have an M, AB. You have an M, BA. You have an M, BC. You have an M, CB, you have an MCD, and you have an MDC. So simply those 2 moments has to be equal and opposite, right? which means that the summation of them is equal to 0. Those are the two moments at point B. The summation of them has to be equal to 0. Those two moments here, their summation has to be equal to 0. So let's apply the first equation here. The summation of the moments at point B has to be equal to 0. Those are MBA and MBC. Has to be equal to 0. Okay? So you just substitute their values, get the values from the equations, okay? Let me grab those here, okay? MBA was 4EI divided by 7.2 theta B plus 86.4 plus MBC, which was 4EI divided by 6 theta B plus 2EI divided by 6 theta C minus 6EI divided by L squared, 6 squared, multiplied by delta. That's equal to 0. It's an equation in two unknowns. What are those? Theta B and theta C. Okay? Theta B and theta C are unknowns here. Okay? So this is equation 1. Or I, equation in Latin. And then the summation of the moments at point C is equal to 0. What are the moments at point C? MCB and MCD equal to 0. MCB was equal to 4EI divided by 6 theta C plus 2EI divided by 6 theta B minus 6EI divided by 6 squared multiplied by 0.03, and then MCD was equal to 4EI divided by 4.5 theta C minus 6EI divided by L squared and multiplied by delta, which was negative 0.03 meters. And that's equation 2. Okay? As you see here, the most important thing that you have to realize here, if EI was not given, okay, you would not be able to find theta B and theta B, because this term here is going to be difficult to solve. It's going to be a function of EI. Okay? So now, just plugging the value of EI that you had, okay, and then solving the two equations. So solving equation 1 and 2, you're going to be able to find theta B and theta C. So theta B is going to be equal to 0.0044 radians, and theta C is going to be negative 0.0345 radians. Whereas EI, we always, had something multiplied by EI when we solve this, right? Now you just plug the magnitude of EI, that's it, okay? We had the magnitude of EI given, so it's just substituted here. So once you find theta B and theta C, what would you do with them?
Plug back in.
Substitute back into equation 1 through 6, and then draw your bending moment diagram and so on, okay? If you do so, just as a homework for you, I'm not going to grade it, I'm not going to take it from you. Just continue solving this problem, draw the bending moment diagram, okay? And then what I want you to do is resolve the problem, okay? Without this relative displacement, without this movement of this support C. And draw the bending moment diagram and see what's the difference, the settlement of support. What changed in the problem due to this settlement of support C? Did the bending moment diagram change? Yes, definitely it will change. Just check that yourself, okay? Any question here? We just have 6 minutes left, so what I'm going to do is I'm going to write the heading of the problem that we're going to start solving next time, okay? And then I'm going to go back to the previous problem, okay? There is something that I want to make it clear and, stated explicitly so that you don't make this wrong on the exam. So now, this is the problem that we're going to start solving next time. we have a member like this, okay? A, B, C, and we have a load here, 8 kilonewtons. It's in the textbook, okay? This is 4 meters and this is 3 meters. And EI is given as 1,000 kilonewtons meter squared, okay? And we're required to draw the bending moment diagram due to the shown loads and a movement of support B of 80 millimeters downwards. Okay. Here, on our next lecture on Tuesday, I want you to solve this problem. Okay? Try solving this problem. Okay? And please don't look on the solution in the book. It's solved in the book. It's exam 11.3. Okay? You know it's in the book. Okay? But that's not the purpose. There is no points for that. Okay? So don't look. I just want to see how you're going to try to solve this problem. Okay? When we start next time, I'm going to ask you. Okay? The only thing that I want to know from you next time, okay? Every one of you, what are the kinematic degrees of freedom here? Okay? So next time, I want you to tell me what are the kinematic degrees of freedom of this problem. Each one of you, okay? And please don't look on the book. There is no points for saying it correctly, okay? I just want to see how you're going to think, okay? That's for this problem that we're going to start solving next time. Now, I just want to move back, okay, to this problem here, okay? The problem that we started this time, we solved half of it last time, and we continued this time, okay? The one with the internal hinge, when we said the shear is equal to 0 here, so the summation of those forces are equal to 0, okay? One mistake, a fatal mistake, that you can do in this problem, okay? And actually, if I didn't tell you this now, I wouldn't blame any one of you to do this mistake. But since I'm telling you that this is a huge mistake, if you do it, it's fatal, okay? The direction of those moments, okay? You're assuming the direction of those moments here, okay? Some of you would say, okay, I'm assuming them, then I'm free to assume them whatever direction I want. No. If you assume those moments in any other direction than the direction that I drew here, you're going to solve this problem totally wrong. Why is that? Okay? And what's the correct assumptions that you have to put? You have to put them in a positive direction, because you didn't know how much they are yet. Okay? You're only going to know when you solve and use the slope deflection equations. So they have to have the same positive direction, okay, as the positive direction of the slope deflection equations. So this has to be clockwise, this one has to be clockwise. If you forgot what I just said and put this as, let's say, okay, this is, you would say, okay, this one is, you expect it to be in this direction, and I expect this one to be in this direction. Just try to do this, and you're not going to end up having the same numbers that we got. And those are wrong. You have to stick to the positive directions of the slope deflection equation. Otherwise, it's going to be wrong. Again, I'm saying this explicitly. There is no excuse for you to do it wrong. Okay? So let me write this here. Okay? Has to be in the positive direction. Okay? It's not an option. This one has to be in the positive direction. Any question? Okay, great. Thank you.
how much the moisture's coming out of it, and then sign everybody's books. Because, Garrett, next Wednesday, and not have these signed. Because he's gonna take them up, I'm pretty sure.
Just never know with him.
I'm pretty sure, because he said next week, I might take them up. Next week, I might take them up. And before he left, he said, next week, I might take them up. To me, that's means he's gonna take them up. Does that not to you?
Yeah.
In concrete, are you always just gonna have the PowerPoints, or will you ever upload the
Just
JMTs?
the PowerPoint.
Just the PowerPoints?
Yeah, because what we write is exactly the same as the PowerPoints, maybe very small differences, so maybe you just can take notes on that. So what I would recommend is maybe you can, I already uploaded all the PowerPoints for all the chapters, maybe you can have them, okay, in your laptop, or you can
Yeah,
print them, and then you take notes on them if you see like there is a difference,
Right. And I've
any
been,
extra thing that you would need to add, just take notes of it.
I've been following, like, just going through on the JMTs, the Windows Grill.
Yeah.
And like the other day, I came late. I just couldn't find parking, and I missed some of that, but I got it put back in. I was just asking for that reason.
Would you like to have them? I have them here. If you want, I can. Do you have a flash drive or something?
I don't have a flash drive with me today in this.
Okay, let me see here. 1 second. You have Windows Journal.
Yes, sir.
Okay, so if I could just send you that file in JNT format, that's going to work for you, right?
That'd be great.
Okay, well, can you just type your email here?
Thank you.
So we actually do it, just.
Okay. So
Even drive.
just put this
No,
concrete and notes,
the Anderson.
and then chapter 3,
I
right?
believe it's the one we just started.
Okay.
Thank you very much.
Yeah.
You have a good day.
Do you want me without a subject? Okay, just.
I didn't tell everyone that.
Okay.
So, get the moisture out of the phone. Thank you.
You're welcome.